Today we're going to talk about recursive descent parsers, and they're recursive, and as Retta said, they're decent. If you want to find these slides or the code that we're going to see, it's in this link. Recursive descent parsers, it sounds pretty scary, but it's not. It's just a category of parsers. And parsers are tools to transform this thing, a string of characters, into something usable, like a data structure, like this, that we can process using a program. And the special thing about recursive descent parsers is that they're top-down parsers, so they will look at the biggest parts of your grammar first, and then they will traverse downwards into the smaller parts. And if they fail to parse something, they will go up one step and try the next sort of alternate way of parsing it. So they will backtrack up the tree. And they are also built from a set of mutually recursive procedures. And what this means is that you can structure your program to mirror the grammar it recognizes, which is very cool. So it basically means that you can, you just describe whatever you want to parse, and it will just parse it for you, which is super cool. So I've used a gem called Parselet to do this in Ruby, which makes life very easy. And yeah, it has a really nice syntax. I've used it to build a natural language time parser that can parse strings like tomorrow at 5 a.m. or whatever. And that's a pretty big parser because natural language is hard to parse. But I recently also built a syslog parser that parses syslog messages, which is a lot simpler. And when I did so, I could just look at the RFC and sort of change the syntax of the ABNF specification into the parselet specification, or the syntax for parselet, and I had a parser that parsed it, which was pretty cool. And we also actually use this for Git shell, so it's been used by many people. Now I'm going to show you how to use this because it's much easier to understand from example, I think. So the first thing we have to do is require parselet. And parselet provides a parser superclass that we can inherit from, like this. And inside of this class, you can access a DSL for defining your grammar. So the first thing you want to do is to define your root element. And the string we're going to parse is going to be this string. It's going to be 1 plus 2 times 3. And we want to parse this into a format that we can use to calculate the result of this mathematical expression. So we're going to call the root node expression. And now we have to define what an expression is. And I'm going to create a rule expression that so an expression consists of either an integer or an infix operation. So an infix operation is, in this case, it's either the addition or the multiplication here. So let's continue and define our grammar here. So an integer in itself is actually a digit that is repeated more than once. So at least once, but as many times as we want. And a digit is actually a string matching the regular expression \d, which is all the digits from 0 to 9. So now we've sort of gone down the full integer path here, but we haven't looked at the infix path. So we have to define those as well. So the infix is actually an integer followed by some space, and then it's followed by an operator, and then it's followed by some more space, and then it's followed by an expression. So as we can see here, this is where we enter the recursion. So this will loop back up here and will match either an integer or another infix operation. So we have some unspecified things here still. So if we run this parser, it will complain. So you have to specify the space, and a space is actually just the string space, like that. And that's going to be more efficient to match than a regular expression because you don't have to run the regular expression. And then we have the operator, which is going to be either an addition or a multiplication. Great. So the addition is going to be the string plus. And the multiplication is going to be the string asterisk. So let's see. Is there something left? I don't think there is. If anyone, unless anyone has any objections, I'm going to try run this. So to run this, we have to create a parser, and then we'll use it to get a tree. So, and we're going to add some debug logging here. So we're going to print out what the parser parse of our string returns. So I've mapped a mapping in Vim to run this Ruby script when I press this key combination. So what we get is an error. So we expected one of integer at line 1, car 1. So our parsing fails for some reason. So let's look at what we have here. We have a string. So let's see what we're missing here. Actually, let's do this instead. What we can do is we can catch the we can rescue the exception that Parselet is throwing here.
Hey, are you doing too much JavaScript?
Yeah. Yeah. So we can catch that or rescue that exception, and we can print out, or we can put out the cos ASCII tree. So this will give us a really nice error, I hope, explaining why we didn't match. So here we get like a tree-like output of what failed. So it started to match an integer and infix on line 1, car 1, and then it had some extra input after the last repetition at line 1, car 2. So we failed to match the digit. Okay, so
is that because we have 1 + 1 space something? Because we're not specifying that we should have a space after the infix, right?
we do. Yes.
Yeah.
So let's see. The digit is repeating. Okay, I'll have to cheat. So we'll look at this. In here, we are doing the same thing, right?
It's the integer rule. You're going to add as integer.
Oh, no, wait.
That's fine.
I think this is the problem. Okay, so I reversed it. So we have to be careful about the order here, because if we start to match an integer, it will match that integer first, and then it will not know what to do about the rest of the input. So what we do is we want to start by matching an infix, and then if we fail to do that, we match an integer. And this is because the infix starts with an integer, which is sort of an off case. But if we run this now, we get some output. But sadly, it's not a tree, as we'd hoped. Instead, it's the same string and some weird @0. And this is the inspect output of the parselet slice class. And a slice is basically just a string and a line number and a column where it matched. So this string matched at line 1 and column 0, and it matched the full string. So it's great that it's matching, but we do want a tree. So to do with this, we have to add some annotations to these rules. So in here, we want to say, for example, that an integer should be matched as integer. So we name this, whatever is matched here, we name as integer. And then we want to name some other things. So in here, we want to name the first integer here as left. It's the left hand in our operation or infix. And the operator as operator. And the expression on the right as right. Like that. Yeah, I think those are all the annotation we need. So if you run this again, we get a totally different output. So now we get a hash. I think, let's see if we can actually print this. Do I have to require pp? There we go. So as you can see, it's a nested hash that has the left hand or the left hand in the addition, the operator as plus, right as the nested expression of 2 times 3. So this is our parsed data, and it's a lot more useful now that we can actually traverse this structure and make something out of it. But it's not the end result yet. So to get to the end result, we have to transform this tree into something more helpful. So to do that, we can use the transform class provided by Parser, and we have to customize it a bit by adding some rules, much like the parser. This time we're not matching a string though. We're matching the parts of this hash. So for example, I can set a rule matching an integer label with the contents, a simple content, and I'll name that content integer. And this, I'm going to transform this. I'm going to replace a hash containing an integer with a simple value in it into something. So if we look again at this output, you see that the integer, there are hashes that they have an integer key and a simple value in there. So that's what we're matching, and that's what we're replacing with this rule. So we're going to replace this with an integer literal with the value, the simple value that wasn't there. So this will be defined as a local inside of this block, and that happens through probably some instance eval or something. It's some magic. So for this to work, we'll have to have an integer literal. And that's going to be a struct with a string, and this will wait with that. And then we're gonna match the rest of this hash. We can actually look at the output so far. So if we take this transform and instantiate it, we can use it, or we can apply it to our tree and get some output. So if we run this, we get some more output below the tree. And as you see here, the integer hashes has been replaced by an integer literal containing a string, which is great. But now we have to match the rest of the expressions here. So we want to match the left operator right hashes that are contained here. So to do that, we'll define a rule of left simple left operator simple operator. So the thing here, why I'm repeating myself, is the first is the label we want to match, and the second thing is what we want to call the local variable in our block. So on the right, we're gonna have a simple right, and this is gonna let's see, this is gonna use the operator. we're going to instantiate the operator with the left and the right. So we're actually missing a label up here, which is the operator. So I'm going to add as addition here and as multiplication here. And then I'm going to define some rules to match those as well. So for the addition, we're going to replace that with an addition class, like that. And for the multiplication, we're going to replace that with a multiplication class. We have to define those as well. So those are also going to be structs. We're going to have a struct new left, right, and struct new left, right. There we go. And so now we'll replace the addition and multiplication hashes with the addition and multiplication classes, so that when we get here, we'll have these classes as the simple operator value, so that we can instantiate it and return an instance of these classes containing the left and the right operand. So if we now look at what we get, let's see. Okay, so for some reason we didn't.
The addition is a typo.
Oh.
The struct.
The struct.
And the where you're defining it on the top.
Like 11.
Yeah.
Oh. Huh.
Action, it's a new thing.
Oh yeah. Okay. Let's see. We're still getting the same thing. So.
Is right a simple?
Sorry?
Is the right a simple?
Not in this case, but okay. So this is an order thing. Since the multiplication is nested inside the addition, we have to transform that first, I think. Nope, not that.
Do you have to do the hash transform, the big hash, left, right, left, off, right, right?
No. Let's cheat again. So let's look at what we got here. We have the same thing. Did I misspell something up here?
In your actual code, you have pass simple addition and multiplication.
Oh right,
Yeah.
You're completely right. Yeah, this is So there we go.
But there, in the example route, it's addition.
Oh yeah, it doesn't really matter. This can be blah, actually,
Okay.
because
Yeah,
it isn't
it's not
used
used,
really. So let's do that instead. There we go. The joy of live coding. I'm lucky I can cheat.
The benefits of live coding.
Great, so now we get a different output. So now we have some nested structs here. So we have an addition with the left operand of an integer literal and a right operand of a struct multiplication with a left and a right as well. So the only thing, so what we can call this is actually an AST, right? So it's an abstract syntax tree. And what we want to do with this AST is to eval it, right? But to do that, we have to know how to eval these things. So the most thing we have is an addition, and we can define eval for this by evaling our left operand and adding it to the evaled right operand. And we can do basically the same thing with the multiplication, but instead of adding it, we should multiply it. And then we have to define the eval of the integer literal. And since what we get is a string, and by adding those we wouldn't get the right result, we want an integer instead. So we can convert our string into an integer using this method. Cool. So if we go back here and add back the out logging, and then we add some logging there, and then we run it, it gives us the number 7, which is the right result, luckily. So as you can see here, you have to know the syntax to do this, but it's if you read this code, it would be pretty describing of what the grammar actually looked like, which I think is very cool. Cool. That is it.
Yeah.
Thank you very much.